So we are techniques and application. So this is going to be following up a lot of what we did in chapter 11. But okay. So the first one, this is, let me show you what we're going to do today. So we're going to talk about this stuff. It won't take too long. And then this is what we're going to work on. This will be your homework. And then the following class day, Friday, right, we're just going to work on this stuff. Okay.
So the homework, what we do, is we're going to work on this stuff.
This will be due.
This will be due, not the assignment.
One more time. We're going to talk about this, right? Then we're going to do this in class, and there's your homework. All right, then look at the next day, day 3. So that means this stuff would have to be due before day 3, right? So then what are we going to do on day 3? Then we're just going to work on these problems. So I just added a few things that, it's almost exactly like your notes. It's just added a few things.
Okay. Oh, so this is why you sent it to us late, because it's not in here. Okay. So this is due Friday.
Yeah, don't worry about then just one day at a time, Ashley. Let's do Friday.
That's all I have to
That's all you got to worry about. So particle in a box. So this is, I jumped down there because we're going to derive that.
Cool.
We will. In our little handout at the end. So, but already they're introducing little n, the little descriptor of the state. And we're not supposed to call them descriptors of states and things. We're supposed to call them quantum numbers. Okay. So there's only one quantum number to describe the state. Okay, it's just one dimension. And so that little n can just be 1, 2, 3. And where does that come from? Well, it's going to come from the derivation of getting that expression. Okay. And it's the particle for energy in a box. And it's the energy. If you remember, we had this expression. What was that for? Expectation values. And omega hat is the operator. So if you want to find energy, then you have to use the energy operator. And that was the Hamiltonian. So that's what we're going to have to plug in to get that expression. Okay, so that's where that's coming from. And what wave function are we going to use? This one right here. Okay, that's the wave function that they're going to give us. Okay. Does this wave function look, if you're going to guess, Ashley, does this wave function look normalized to you? To me it does. Because look, I've got the x inside the sign, and I've got some constant out front. So I don't know if it's normalized. You'd have to set up the integral and prove that it's normalized. But if I was going to guess, I'd say, man, she looks done. I don't have to normalize it. I bet you they're going to let us use that. But I don't know. We'll find out. See, a box between x can go from 0 to L. So here's that funky box that they're talking about. Even though it's only one dimension, it can only be between 0 and L. Okay. So why do they make these walls so high? It's just energy, right? Saying that it's infinite. It has to be in there. You can't get out. Okay. It's like if you had a little dude on a hill, right? You got a high mountain or whatever, and there's a little, I don't know, roll the little ball down into the hill. Right? It just ends up rolling down here, right? Doesn't have enough energy to get out of there. And this is infinitely high, right? So it just ends up being on the bottom. So I don't know if that helps you picture anything, but okay. What else is in here? Oh, we have little m. Richie, little m is probably what in this? The mass of the ball or particle or whatever the heck is it that we're talking about. Probably an electron, right? Okay. L, the length of the box. H, Planck's constant. Okay. let's check something out here. Oh, we'll get when we get over there. So here's our wave function that they're just going to give to us. Okay, separation of energy levels. So n can only be 1, 2, 3, 4, 5, 6. So if we want to know the energy difference between, I don't know, 3 and 4, between n equals 3 and n equals 4, hey, what's the energy difference for this particle in a box, right, for the different energy levels? What would you use for n in this expression? Right? Because n is, you want to know the energy difference between the n equals 3 and n equals 4 energy state. So it seems like this equation is going to fit perfect. But there's only one n. Which n do you use? 3, right? Do you see why?
It's because that one's +1.
Because this one's +1. Exactly. That's how you're supposed to see it. So you have to use the lower one. Okay. Good. Let's check out something here. Okay, so I want to click on this bottom energy level. No, we don't want to mess with time, right? And this is what the wave function would look like for the bottom energy level, or the probability density. Which one kind of makes more sense to you? Wave function or probability density? Which one has more meaning to you?
Probability density.
Why? Why?
Because it tells you the probability of the particle being where you want it.
Exactly, where the amplitude is maxed out. Yeah, wherever you see positive amplitude, that means where it's supposed to be. This doesn't really mean anything, right? It's just but it's got a lot of information in it, but it doesn't really mean anything until you find the probability density, right? So I'm going to keep this one being plotted, okay? And if we see what happens to the probability density as you increase the state, you get more, what are they called? It's just an n. You get more nodes. This ends up being a standing wave, right? Okay. So we could actually plot these things out. The wave function looks like this, but okay. So what's kind of interesting to me here, if I jump back down here somewhere, like to the second one, if I change the width, right? What does it look like these energy levels are? Are they equally spaced? Right, they're trying to show these are the energy levels. Do they look equally spaced? No. They look like they're getting wider and wider as you go up, right? So if I make the box longer and longer and longer, what happens to the energy levels? They get, well,
They become closer together.
they become closer together. So,
Your energy level density increases.
so if you, yeah, the energy spacing is much, much smaller. So if you make L huge, right, like a macroscopic object, because you can put it a ruler and measure it. That's macroscopic. And you put a ball in there, it doesn't roll in this position, that position, right, and appear here, there, and do these funky things. No, it just rolls around in there because the energy levels are so closely spaced together. It's like a continuum. You can't tell. There's no quantization of energy. Okay. Okay. So quantization, I think, becomes more and more important as you make this box more and more narrow, right? So as you make things smaller and smaller and smaller, that's really when quantization shows up in the first place. So that kind of fits. Okay, let's see what happens. Make it, whoa. It should let me. Maybe this one? There it is. Yeah, it doesn't do a whole lot, does it? No. Yeah, because once it's this is not an infinite box. Once it gets out of there, once it has more energy than that height of the box, it's out. It can take whatever energy it wants. So that is a really good idea. If you get more energy than E5, whatever the 1.75, I don't know what their units are in this, but If you give it more energy than that, the particle can take whatever speed it wants. It doesn't have any boundary conditions. So boundary conditions is this well, this potential energy well. That's what creates quantization of energy in the first place, are the boundary conditions. That's the technical word for it. The borders where this thing has to be. If you have those borders, energy has to be quantized. You remove those borders, but they don't want you to call them borders. They want you to call them boundary conditions. Remove those boundary conditions, right? Make this guy remove the boundary conditions. There isn't any quantization of energy. So boundary conditions are key to this whole story about quantization of energy. Yeah, here it is, right here. So boundary conditions are the reason why energy is quantized in the first place. Without them, you can't have quantization of energy, right? Without these walls, the electron can do whatever the heck it wants. There's nothing keeping it, and there's nothing constraining it. Okay. Yeah. Because if there aren't any constraints, that electron can take whatever speed it wants. It's kind of like a weight on a spring. You remove the spring, you remove the whole problem. There isn't any problem anymore, right? There's just a weight. So there aren't any conditions anymore. So notice how these things kind of made sense. If we made L much, much larger, right, the energy spacing gets much, you're dividing by a much, much bigger number, much smaller. And we saw that. The mass. If you make the mass much, much larger, the energy spacing becomes smaller. And that makes sense too, because if you want to extrapolate to baseballs, well, yeah, compared to the mass of an electron, you can't see that energy spacing. I wonder if that animation showed that. Whoop, I kind of screwed this whole thing up. Where did it go? Can I mess with mass? I don't think it lets me. I can't pick different particle. Oh, here, particle mass. There it is. No, it doesn't let me do much. I can make it. See, I can make it. I can make it smaller, and see how the spacing got bigger. All right, make it more massive. I wonder if I can type in. No, it won't let me. Okay. 0-point energy. Oh, I shouldn't have erased that box. But you saw all those lines in there? There wasn't one at, you can't have 0 energy, because the lowest number is n equals 1, right? So it's not n equals 0. So at the ground state, the lowest energy, it's not 0 joules. So even when in the ground state, there's going to be, probability and all the things that we've calculated before.
So even when it's at rest,
there's motion, there's probability, there's a state, and
So in other words,
there's always going to be energy. Yeah. There's always going to be energy. So that Heisenberg uncertainty principle works always, even if you're in the ground state, the lowest energy possible. Let's see. Okay, now this is kind of odd to me, because if you we saw that these energy levels got more and more highly spaced, right? So if I got rid of this and I just made it go infinitely high, right? These energy levels should be spaced even more way up there, right? Because it's supposed to get, energy spacing gets larger the farther up you go. Well, the correspondence principle says that you're going to reach a continuum of states. But I don't get it, because it's even more quantized up there. So this is something that I've never really quite followed. I can see continuum of states. You can't see the energy difference between the states. That's when, yeah, if you would block this off and remove the well, Yeah, here you have a continuum. But way up here, see, remember, these are going to infinity. So they're saying way up here, there's a continuum of states. I don't really see that. If someone could explain that to me, that'd be awesome. Okay.
So you're saying up there's an
There, yeah, continuum number of states. That it's the energy levels are so close together, you can't tell the difference. But they're getting farther apart. So I don't get it. That's something I still am trying to figure out. But anyway, so let's just keep going here. We have orthogonal. Okay, if we have, so notice how you could be writing, you could take a look at this equation for the particle in a box, and you could write stuff like psi1, right, and write its expression. You just put in a 1 for n then, a 1, and then you could write psi2, right, and write its expression. Okay, and what they're saying is that here they wrote psi1 and psi3. It doesn't matter. They just have to be different. Then those states are orthogonal. And what that means is if you plot them out, right, like this is what psi1 looks like if you plotted it out. Okay, here's your box length L, right? Has to be between those two. If you plot out psi3, it looks like that. So those are the wave functions. But probability density was you had to multiply them together, right? And you always do complex conjugate of the first one. And if you multiply two of these wave functions together, right? Pick any two. I don't care, any two you pick. Pick any two. Pick two ends, plot them out. They're always going to be orthogonal. In other words, you add up the areas, it's going to be 0. If you multiply psi1 times psi3, you get the green dude. Well, look at the area. You've got positive area, positive area. We have negative area down here. It exactly cancels out every single time. So they call these states orthogonal. So that might be a homework question. I'm not sure. But it would be a good one because pick any two ends and find their probability density. That probability, that number is going to be what? Every single time. Because integrals are area. 0. Because area is going to be 0 overall. So you're going to get 0 every single time.
That's funny, but that's...
But an advantage of it, a huge advantage of it, is Spartan. Spartan takes advantage of that big time. It doesn't have to calculate these integrals. It just recognizes orthogonal states, doesn't even calculate them because they're all zeros. It gets a lot of integrals out of the way. So that's an advantage, but we'll get into that more later. You have a question? See, here's that correspondence principle again. You see that? See how the energy level spacings are getting bigger and bigger and bigger? And then as you get really high ends, classically allowed energies, then that means continuum states. You can throw a baseball whatever speed you want. So there's a problem here. There is a problem here. Quantum mechanics isn't working, right? It only works for microscopic objects. You got to stay away from baseballs. It only works for the microscopic level. And you got to have boundary conditions, otherwise there's not a problem in the first place to solve. So life is not all hunky-dory here. But when you do talk about the microscopic world, quantum mechanics has yet to be proven wrong, but it's definitely wrong at the macroscopic world. Okay. Where are we here? 2 dimensions. Okay. I don't think we need to worry about this too much. They're just trying to say that if you did 2 dimensions and solve this whole particle in a box problem, which I don't think we're going to do, but it's just a concept, you end up with this expression. You end up with 2 quantum numbers, and it ends up looking like I'm trying to read my own writing here. N1 squared over L1 squared. So there's two dimensions, L1 and L2. Now you actually do have a square that it has to be in. All right, so L1 and L2. And what is it times h squared over 8m? So I wouldn't worry about this too much. Their point, all they're trying to get out of this, though, is this idea of degeneracy. In 3 dimensions, it's triply degenerate. So what's the degenerate mean? It means you have the same, for example, if you plotted energy, and I said, this is the energy level for 3p. How many orbitals did you draw?
Red.
3p has how many orbitals? 3.
6. I don't know.
You can fit 6 electrons, but it's triply degenerate.
Yeah.
There's 3 states, all with the same energy. So now you've got this nice little equation for energy, right? And you do, all the game is just play around with the quantum numbers n1 and n2, and if you get the same energy more than once, it's degenerate. So you could pick, for example, n1 could be 1, n2 could be 2. I'm just picking any numbers. That's a state, right? Because you give values to these quantum numbers, you're describing a state. And you could plug in those numbers and get the energy. Well, I could switch them around. I could make n1 be 2 and n2 be 1. Different state, because they have different set of quantum numbers, but the same energy. So it's degenerate, doubly degenerate.
So you don't square n2, right? It's just plus n2.
Oh, I didn't write a square there. The equation really doesn't matter because I don't think we're going to use it.
Okay. Yeah, I was just.
It's just an
wondering.
idea.
I was just curious. I didn't see it first.
All right. So if you had 3 dimensions, you'd have triply degenerate. Okay, for a particle in a box. And
over L1 plus N2 over L2 plus N3 over L3.
yeah, yeah.
Is it square? Is it H over H squared over 8m?
I'm pretty sure it is.
Cubed?
No, it's always h squared.
Okay.
I'm pretty sure it is. We didn't get that. I don't even think that's in the book. That sounds right. But see, that's one of those dimensional analysis things that screw you over, that don't count. You actually have to prove it. So I'm just guessing. Okay, so tunneling. I kind of was drawing a little picture of this, but if you have a little dude, he's got his little ball, right? A little mountain. All right. So he rolls his little ball. There's no way he can, right? This is supposed to be a mountain. I'm not very good at drawing, right? He kicks his little ball and just ends up rolling in here back and forth, right? There's no way the ball has energy to go over the mountain and get to the other side. Even though, oh, I should fix this. Even though, oh, I erased the whole thing. Even though on the other side, right, it's even lower, right? Nature says the ball would like to be down here, lower potential energy. But it doesn't, right? It doesn't have energy. It's a ball. It's a ball. It's a ball, right? Okay. So same problem, but make everything the size of an electron. Now the electron has a wave function. And the wave function, it actually has an amplitude out here somewhere. If you would kind of, oh, it's drawn right here, right? This is your mountain. And the wave function kind of goes through the mountain a little bit, and it has some amplitude over there. But remember, wave function doesn't mean much. You have to probability density, square it. So, no, they didn't do that. They didn't plot it. But you'd end up with some positive area over here, right? If you did the probability density. So if it was the size of an electron, there's a probability that the electron, that little ball is over here. Does that mean that it went up and over the mountain? No, it didn't have to. So it's a wave. It went straight through it. Moreover, that little ball, that little particle, could be inside the mountain. It's a possibility. You could find it there. Now, these aren't very high probabilities because look at the area. It's extremely small in comparison to the area on the inside of the box where the ball's supposed to be. You do this experiment a gazillion times, you're going to be measuring it every single time over here. But there's a chance. There's a probability that it will be over here. Just like winning the lottery. It's pretty much the same. It ain't going to happen, but everyone likes to believe it will. But it's a possibility. You know it's a possibility. It's a possibility it's found inside the mountain. So that's tunneling. Very odd stuff. But it has to be there. That possibility has to be there when you take it into account. Okay. So here we go. I say we set these up as much as we can, and then you can finish them at home. I think setting them up is the hard part. Trial wave function. That looks so... Man, I wonder if that was on here. We did something like that on this exam I'm handing back.
The child wave function.
Oh, it is. It is. The same one. Yeah. So this is the exam question. Look at the very last exam question.
Okay, cool. Exam question. I'll skip that one.
All right. Look at the last exam question. Okay. So, but just to get you, just in case someone had no idea on there, most everyone did really good on this kind of stuff, though. Right? Yeah, on the math. This is your starting point. Right? That's your starting point. You put in the limits and what d tau is and the wave function, and you're done. Okay. You put in the normalization constant. Okay. 2. Calculate the average momentum for a particle described by a normalized wave function. Oh, we need the normalized wave function. Oh, I wonder if someone got it right. Okay. You should get this.
I do.
See if you remember this. 30 over L to the 5th square root. That's your normalization constant. And then your function again. Okay. So there's the normal. Hopefully you get that as your answer. Okay. Work that out, number 1, and hopefully get that as your answer. Assume you got that. Good. So we're doing number 2 down here. Average momentum. Now, average anything.
Oh, do we still have to do 1 over again?
Well, you're going to have to do it, yeah.
Yes? Okay.
Yeah. Yeah, you got to show your work. Okay, so average anything with that observable thing, right? Momentum was p hat. Okay. So, well, just so you don't forget, this is the format I'm copying. Psi star. All right. Everyone agree? All right, here's my observable. We put it in the middle. Okay. So all we have to do is look up what the momentum operator is. Isn't it P has h bar over I d dx, if I remember right. But I need to write my wave function. And then write the wave function again. And there's no I to worry about, so no complex conjugate. Just write the wave function. It would look like that. H bar over I. This is my starting point. This implies, this is how you'd write it. All right? This means implies. So we pretty much just take the derivative. What can we pull out of this integral? Well, what are our limits? 0 to L. So we can put those in. D tau is dx. What can we pull out of that integral?
30.
Yeah, 30 over L to the 5th. Good. What else? Well, that has an x in it.
That's right.
One more thing.
Can you pull out your HIDX?
No.
Can you pull out h bar over I?
Yeah.
No.
What is h bar?
Planck's constant.
Planck's constant divided by 2 pi is h bar. But it's in the cheat sheet. Okay. And I is what? Square root of -1. Are either one of those x? No. So can you pull it out of the integral?
Yes.
Yeah. So we'll pull that out of the integral too. Okay. So pretty much you just need to take the derivative with respect to x of what?
Of 1. Or any constant.
What's left? If you pull this out, you just have d dx in front of this. So you
it's
have
allowed to be 1.
you have to take the derivative of this with respect to x. What would you get?
X squared over 2 minus x 3 over 3.
What's the derivative of xl with respect to x?
Oh, derivative.
L.
X squared divided by 2.
Yeah.
L minus 2x. Right? Take derivative of xl, you just get L. Take derivative of negative x squared, you get 2x. So it would be L minus 2x. All right? So then you end up with the L minus 2x. You're going to have to multiply that by this guy, right? And then do your whole antiderivative bit, and you'll have an answer. And yeah, your answer is going to have an I in it and an H bar. That's how it is. Okay. So that's 2 is set up. Let's see if we can set up 3. Average energy. I'd like to have that cheat sheet. I'd feel much more comfortable if I knew you guys had these operators on that cheat sheet. So you got your cheat sheet. I don't have mine. Is it on there? Pablo, is it on there? Is P hat on there?
Yeah.
It is? How about the energy operator? Is that on there? What was the energy operator?
The omega hat equals the W thing times F.
Oh, you're thinking. This is on the cheat sheet, but that's the definition of an eigenfunction, eigenvalue. That's a definition of that. I'm trying to catch up to where you guys are at. So I need chapter 12 cheat sheet.
Oh, yes.
No, I'm just tearing mine out here if I can find it.
No, so we take the second derivative.
Where the hell is it? Page what? Oh, I think I already tore it out. I already tore it out. Yeah, I found it. I found the bloody thing. Okay, so hopefully everyone's looking at page 22, right? Okay, let's make sure. Okay, good. The momentum. So how can you recognize operators in the first place? They're supposed to have a what on them? A little hat. So do you see a typo on this?
Yeah.
Yeah. What should have a little hat on it?
The H.
The H. Because that's our energy operator. I gotta fix that.
Planck's constant should have an H on it.
No. Show them, Pablo.
This one.
That capital H.
Oh, okay.
That's our Hamiltonian operator, right?
Both of them?
Where it's h bar negative h bar squared over 2m d2 dx squared plus v of x. That's the energy operator. Okay. So since it's an operator, it should have an h on it.
Not sure about
I don't think it's all of them.
how
Okay. So wherever you see this capital H,
Oh, there you go.
You should have a bloody operator, the bloody hat on it. He should have a hat because that's what he is.
So overall, the capital.
Wherever you see a capital H, he should have a hat.
So there are 3 missing.
Yeah, you should have 3. You have to draw 3 hats. Okay.
How would you read that one that says H equals negative H bar squared over 2m?
That's a del. We're not there yet. That's 3 dimensions.
Oh, okay.
So you still only has 2 dimensions on the box.
I was just trying to figure out if that's supposed to be the second derivative
No.
or something. But
Well, it's a second derivative. It's d2 dx squared plus d2 dy squared plus d2 dz squared.
Oh, okay.
So they just don't have to write all 3 of those. That's why they write it. It's kind of silly, but that's what they like to do. Looks better on a T-shirt. So integral 0 to L.
Which one? The ones people didn't buy?
Right? We need to, because number 3 wants calculate the average energy. So that's why I picked this one. Okay. Now since we did notice we drew 3 hats on here, what are we going to plug in for the energy operator? What are we going to plug in for it? You have to write your wave function. Which one? How many dimensions do we have? We just have one. We just have x, y, or z. We just have x, right? So it's right there. It's the very first one, the d2 dx squared. If it was all 3 dimensions, it'd be the one that Ricky was worried about, the del. Okay. So you pretty much have to copy it just as it's written. Well, h bar squared over 2m.
So we want to also look for a 2D operator?
d2 dx squared. We don't have one. Essentially, all we have something written for is 1 dimension and 3.
Okay.
So I guess we won't see any 2-dimensional problems. Well, if we did, it would just be plus d2 dy squared. It wouldn't be any big deal.
Okay.
Okay, and then plus v of x. Now I think, though, it said that this v of x is what? 0. Now, do you see that? That's how these boxes are, because this is v. And when you're inside the box, v is 0. All right, so that's what we've been doing. So v is which energy? Not kinetic, but potential. V is the real problem in solving things with Spartan and everything else. V is the potential energy that's like the 3-dimensional potential energy surface that an electron feels as it's moved around in that bond in that molecule. So that really complicates the calculations. So it's really nice to make it 0. We can actually do it on our own then. Oh, and I have to write the wave function again. Okay. So we'll pull out what we can again. Okay. And that's going to leave xl minus x squared here.
Sure.
Yep.
That's your 1/2 on the 30,
Why 1/2 on the 30?
30.
Oh, thank you, sir. 1/2. Yeah, that's the square root. Okay. So you see how we'll have xl minus x squared here, because we can't pull that out of the integral. We'll have what left in here?
D squared.
d2 dx squared, exactly. We'll have that left in here. And what we'll have over here, we'll have this xl minus x squared. So pretty much what do we have to do now? The next step would be take the first derivative of this, then be anal about your notation. So when you do this, you should be writing, you'll have all that stuff we talked about, but you should write d dx, and then the result that you got, right? Otherwise, you're going to forget to take that second derivative. So you write d dx, and this inside here will be L minus 2x. And then the next step, the d dx is gone. And you're just left with -2. Right. And you just pull it out of the integral. And you have a dx at the end on all this.
That's cool.
Okay.
I know you did the inside of the integral.
Okay. You got to do what the little rule maker operator says. So you can do anything, depending what that rule is, the operator. That was 3. That is 4. Okay, 4. So here they're giving us, all they're doing is changing the wave function to a much better wave function. And they're saying calculate the average energy. So you would set this up in a very similar way as to which question? Number 3. It's identical. Yep. Except I think right, it's not this nice.
-2.
Yeah, you're not going to do this nice -2. You're going to have a sign, because you take the second derivative, you're going to end up with sine again, right?
Yeah.
So you're going to have the integral of a sine square. It's back to that little, what is it called, the half angle formula or something,
Yeah.
right?
Identity.
The trig identity. So you'll have to use that. So see how far you can get. We've got some time here. Knock this stuff out. I can help you out while we're here.
So we're just supposed to put. How do we know which operator to use here?
The only clue you have as to which operator is they say calculate the average, then whatever word is next, that's the operator. Calculate average anything is always an operator because it's over an integral over all possibilities, all states,
Oh, okay. And
all
the
positions.
H, the one with the H hat is energy.
Energy. And p hat was momentum, linear momentum. I think that was about it.
Okay, so for right now, linear momentum and how did we know that VCX was equal to 0 because V was 0?
They said it in the question.
Oh, they did?
So those are the only operators we've done is momentum and
And energy.
Which problem was that where it said that it was, oh, there, 3. Okay.
Yeah. So we'll assume it's 0 also for number 4. You have to. So yeah, you can knock out a couple of these, I bet.
Yeah, I'll get
Oh, we can hand back the exams.
that's all.
Let's do that.
Yeah. Thanks for waiting until the end of class so we could focus on this stuff instead of our rage. You know, I don't know that because for instrumental we only had one exam.
All right, so
96 points.
I don't want to look.
yeah, out of 96. I don't have it. I don't have an exam here, but so
Just missed it.
the final is I take it off of these exams. So let's just go through the answers quick here, right?
Oh, the finals on these exams?
The finals on these exams.
So how many exams total do we have?
Depends how far we get. There's one after each chapter.
Okay. And the finals just you set out the exams.
Yeah, it's just another exam.
Comprehensive.
So are there any questions on the first page?
yeah, can you do number 5, the correct answer?
5. Okay. To normalize a wave function, I'm just copying these right from I think from the cheat sheet.
Yeah.
But and there's a lot of different ways to write this. I would accept this. I would accept n phi star n phi, right? dx or whatever. But this is generally the starting point. Expectation value. again, from the cheat sheet.
I don't think that was on the one you gave us, for the test. Yeah, I noticed that the expectation value, I don't think was on there.
Oh, yeah?
Yeah, the one you gave us was a bit different from ours. Yeah, it was missing something.
Oh, that's not good. Normalized wave function. But regardless, that's the that cheat sheet, that equation sheet was different than the one you used for your homework?
Yes.
Oh, that sucks. Should have been the same thing.
Yeah, I think I'm pretty sure the normalized one wasn't on there. But I mean, I memorized it from you.
Well, this you should know.
Yeah.
Okay.
And I don't think the expectation value was on there either.
Well, it was also in the homework though too.
Yeah, that's something we
A function is an eigenfunction. That was operator, function, right? Yeah. They're not on. They're not on there. But they weren't on here either, so. This is the one that you were studying from.
I'm so anxious to see number 9.
Okay.
You mean number 8?
No, number 9.
Oh, you actually want the bottom one?
Yeah.
Number 9? Well, let's just do number 8 first, since that's the next one.
Since everybody wants to.
8 is,
I mean number 9. I want to see where I got this one.
let's see.
Oh, why you got it?
1 over x.
Yeah, I got that one on too.
Well, you take the derivative of 1 over x, you have another x. You have x to the negative 2. You just change your function.
Oh, no, can I see it up there though? Could we do
Okay.
it like
Well, let's
x
just,
to the
okay,
negative
let me
1,
get
right?
let me
Once
get
we
this
do
one
this,
first.
once we do this.
I just wanted to show you that this guy, 'cause if he's not in the homework, then I screwed up, right? There it is right here. No, that's not it. Yeah, it is. It's question homework. It's exercise number 2. Yeah, exercise number 2. It's from the very beginning of the first homework assignment.
Yeah, I got that one on. Just gonna look at it.
Okay, so
Exercise number 2.
yeah, exercise number 2. Exercise number 2. And then in number 9, you wanted to see which one?
1 over x.
1 over x. And it was, what was your operator?
Just d squared over
d2 dx squared. Okay.
That should be negative x to the negative 2 there.
Right?
It should be negative x to the negative 2.
So,
by the
but-
time you get to d dx.
The negatives are going to disappear on you. So, but regardless, you have a different function because it has to look like this. You have to have a constant times your function, not a function times a function. To get your function back, it would have to be 1 over x. So,
Oh,
so you have 1 over x. Yes, you're right. You have 1 over x here.
That's why, okay.
But this is not an eigenvalue.
Okay.
That's not a constant.
It can't have x in there.
It can't have x.
I never knew that. Now I know.
Okay, it can't have x because it's not a constant. That's a definition of a constant. No x.
So it's not.
Wow.
Okay, cool.
How about the next one? Were there any others in there?
Dr. B's about? No, I can see why I got these wrong, I guess.
How about the next page?
Got that right. I'm good. I'm good. Yeah, it was just a concept. Most of the math is alright.
Yeah.
We're gonna have like 5 tests, right?
It usually is, yeah.
Okay, so 8 is exercise number 2. Okay.
Let's do an extra test if it'll help out.
We can always go faster, then you can have more tests.
Oh yeah.
Yeah.
Very nice.
That sounds good.